Namaste, my friend, and welcome back to JEE Chemistry with Typical Monk. This is Class 8, and today we open one of the most beautiful chapters in all of physical chemistry, thermodynamics. Here is the single idea that runs beneath it all. Energy can flow as heat. It can be spent as work. It can change its form again and again, yet the total is never lost, never created. The universe keeps a perfect ledger. When David first heard this, he asked, "So where does the burnt candle's energy go?" Nowhere and everywhere. It simply changes form, and the books still balance. And in G, this same ledger grows sharper. You will learn to compare reversible and irreversible work, chain Hess's law into numbers you can check, and count bonds correctly across a full combustion reaction. Today we learn to read that ledger, energy's bookkeeping. Take a slow breath. Let us begin. So what will you carry home from today's class? First, the vocabulary, system and surroundings, and the deep difference between a state function and a path function. Second, the first law itself, delta U equals Q plus W, its sign conventions, and how reversible work compares with irreversible work. Third, enthalpy H, the relation delta H equals delta U plus delta ΔngRT, and the neat little result Cp minus Cv equals R. Fourth, Hess's law, and the harder G-level bond enthalpy numerical built on a full combustion reaction. And fifth, the G drills. Assertion and reason match the column, and a numerical quick check. Ready? One idea at a time. Before any law, we need the language. First, the system is the part of the universe we choose to study. A reaction in a flask, say. Everything else, the flask, the room, the rest of the cosmos, is the surroundings. Draw an imaginary boundary, and thermodynamics begins. Second, systems come in three kinds. An open system exchanges both matter and energy with its surroundings. A closed system exchanges only energy, not matter. And an isolated system exchanges neither. A perfect thermos flask is the closest picture. Third, and this is the heart of the chapter, a state function depends only on the current state of the system, not on how it got there. Internal energy, enthalpy, temperature, pressure, volume, all state functions. Like your altitude on a mountain, it depends only on where you stand, not the trail you climbed. Fourth, a path function depends entirely on the route taken. Heat and work are path functions. Two different roads between the same 2 points can cost very different amounts of heat and work, even though the change in a state function is identical. Hold that contrast. G tests it every single year, and it is exactly what makes reversible and irreversible work different, even between the same two states. Now, the first law, and look carefully at this diagram. The golden box is our system. The dashed flame around it is the surroundings. The law is simply this: delta U equals Q plus W. The internal energy of a system changes for exactly two reasons: heat crossing the boundary and work crossing the boundary. Nothing else. Energy is conserved. Now the signs. And here is where marks are won or lost. Heat absorbed by the system, flowing in, is positive Q. Heat released by the system is negative. See the green arrow pointing into the box. That is positive heat. For work, the convention we use is this: work done on the system is positive W, and work done by the system is negative. The green arrow pushing in is positive work. And now the G twist, sitting in that dashed violet box. When a gas expands against a constant external pressure, that is irreversible work. W equals minus P times delta V. But push the same gas from the same starting volume to the same final volume reversibly in tiny isothermal steps, and the work done is W equals minus nRT times the natural log of the final volume over the initial volume, and its magnitude is always the larger of the two. Same start, same end, different path, different work. No, the gap is the single most examined idea on this slide. Now enthalpy, the quantity chemists actually measure in the lab. First, Enthalpy is defined as H equals U plus PV. Why invented? Because most reactions happen in open beakers at constant pressure, and at constant pressure, the heat exchanged is exactly delta H. So delta H is the heat of reaction you can measure directly. Second, contrast that with constant volume. If the volume cannot change, the system does no expansion work, so all the heat goes into internal energy. Delta U equals Q at constant volume. Third, for reactions involving gases, the two are linked by delta H equals delta U plus delta ΔngRT. Here delta N gas is the change in the number of moles of gas, products minus reactants, and G will hide a sign trap in exactly this term, so read the equation twice before you commit. And fourth, a keying result for an ideal gas. The molar heat capacity at constant pressure minus the molar heat capacity at constant volume equals R. That is, Cp minus Cv equals R, the gas constant itself. Simple and very examinable. Time to solve a full G-level numerical together. Slowly, the monk's way, and this one is harder than the two-atom version, because we must count bonds correctly across a whole combustion reaction. We will find the enthalpy of methane plus 2 oxygen giving carbon dioxide plus 2 water, using bond enthalpies. Step 1. Write down what is given. The bond enthalpy of carbon-hydrogen is 414, of oxygen-oxygen is 498, of the carbon-oxygen double bond is 799, and of oxygen-hydrogen is 464, all in kilojoules per mole. Step 2. The formula. Delta H equals the sum of the bond enthalpies of bonds broken, minus the sum of the bond enthalpies of bonds formed. Step 3. The bonds broken. One methane molecule holds 4 carbon-hydrogen bonds, and we break 2 oxygen-oxygen bonds. 4 times 414 plus 2 times 498, which is 2652 kilojoules. Step 4. The bonds formed, and here is the trap G loves. Carbon dioxide is not one carbon-oxygen bond, it is 2, and 2 water molecules give 4 oxygen-hydrogen bonds. So we form 4 carbon-oxygen bonds and 4 oxygen-hydrogen bonds. 4 times 799 plus 4 times 464, which is 5052 kilojoules. Step 5. The answer. Delta H equals 2652 minus 5052, which is minus 2400 kilojoules per mole. Exothermic and a clean round number precisely because we counted every bond honestly. Now one of the most elegant ideas in the chapter, Hess's law. And this time, we put real numbers on the cycle. First, the foundation. Enthalpy is a state function, so the total enthalpy change depends only on the starting and ending substances, not on the route between them. Second, the direct path. Carbon plus oxygen budding state to carbon dioxide releases 393.5 kilojoules per mole. Third, an indirect path to the very same carbon dioxide, going first through carbon monoxide, has 2 steps. The first releases 110.5 kilojoules per mole, and the second releases 283.0 kilojoules per mole. Fourth, and here is Hess's law in numbers, the direct change must equal the sum of the 2 steps. Minus 393.5 equals minus 110.5 plus minus 283.0. So, if a reaction is hard to measure directly, like carbon burning only halfway to carbon monoxide, we build its enthalpy from steps we actually can measure. And remember, reverse a step and you reverse the sign of its enthalpy. That single trick unlocks a whole class of G questions. Now sit up straight. These 5 lines are what G actually asks, year after year. 1. The first law, delta U equals Q plus W bully. Heat flowing into the system is positive Q, and work done on the system is positive W. Memorize both signs cold. 2. Between the same 2 states, reversible work is always the larger in magnitude compared with irreversible work. G loves testing this through an isothermal expansion numerical. 3. Delta H equals delta U plus delta ΔngRT. and delta N gas is products minus reactants, flip that sign by mistake, and your whole answer flips with it. 4. Hess's law, simply add the enthalpies of the steps to build one you cannot measure directly, and if you reverse any step, reverse the sign of its enthalpy. 5. The standard enthalpy of neutralization of a strong acid by a strong base is a fixed number, minus 57.1 kilojoules per mole, because it is really just the formation of water. Learn that value. Let us drill the G way. Remember the 4 options. Option A, both statements true, and the reason explains the assertion. Option B, both true, but the reason does not explain the assertion. Option C, assertion true, reason false. Option D, assertion false, reason true. First one, assertion. Internal energy is a state function. Reason, its change depends only on the initial and final states, not on the path. Think like Sada, check each on its own, then check the link. Is the assertion true? Yes. Is the reason true? Yes. And does the reason explain the assertion? Perfectly. Being independent of path is exactly what makes something a state function. Both true. Reason explains. Option A. Second one, assertion. Between the same two states, a reversible isothermal expansion of an ideal gas does more work, in magnitude, than an irreversible expansion. Reason, a reversible process occurs through an infinite number of infinitesimally small steps. Now pause, because this one is subtle. Both statements are true. But does taking infinite tiny steps by itself explain why the work turns out bigger? Not quite. The real reason is that a reversible path keeps the external pressure matched to the gas's own pressure at every instant, so it always resists more and extracts more work. Infinite steps is true, but incomplete as an explanation. Both true. Reason does not fully explain. Option B. This is the trap that catches John every time. Third one. Assertion. For nitrogen plus 3 hydrogen giving 2 ammonia, delta H is less than delta U. Reason, delta N gas for this reaction is plus 2. Check the reason first. Moles of gas on the product side are 2. On the reactant side are 1 plus 3, which is 4. 2 minus 4 is minus 2, not plus 2. So the reason is false. Now the assertion, since delta N gas is minus 2, delta H minus delta U equals delta N gas RT, a negative number, so delta H truly is less than delta U. The assertion is true. The reason is false. Option C. A quick match now. Say each answer aloud before I reveal it. The first law of thermodynamics, delta U equals Q plus W. The conservation of energy, written for a system. Enthalpy, H equals U plus PV. The heat content chemists measure at constant pressure. The heat capacities of an ideal gas, Cp minus Cv equals R. The gas constant, exactly. And the link between enthalpy and internal energy, delta equals delta U plus delta N gas RT. If all 4 came to you before the reveal, the chapter is becoming yours. Use a favorite G format. I will read some statements. You silently count how many are correct. Statement 1. The magnitude of work done in a reversible expansion is always greater than or equal to that in an irreversible expansion between the same two states. Hold your verdict. Statement 2. Work is a state function because it depends only on the initial and final states of a system. Think carefully before you answer. Statement 3. The standard enthalpy of neutralization of any strong acid with any strong base is nearly the same, close to minus 57 kilojoules per mole. So, how many are correct? 2 statements, the first and the third. Reversible work truly is the larger or equal in magnitude, and strong acid strong base neutralization truly does settle near that same fixed number, because it is essentially just water forming. But the second one, false. Work is a path function, not a state function, the exact opposite of what it claims. Now let me save you some marks. 2 myths that trap thousands of students every year. Myth 1. When a gas expands, the work done shows up as positive W in the first law. It feels natural. The gas is doing something, so surely it is positive. But here is the truth. Expansion is work done by the system on the surroundings, so it is negative work. W equals minus P delta V. The system is spending energy to push outward, and spending must carry a minus sign. Myth 2. A reversible expansion and an irreversible expansion between the same two states must do the same work, since the change in volume is identical. The truth, they never do. Reversible, quasi-static work is always the larger in magnitude. Only state functions like delta U and delta H ignore the path completely. Heat and work never do, no matter how equal the volumes look. Time to test yourself, rapid fire, and today one of them is a real numerical. Here is the rule. I ask, you answer in your head before the reveal and spell each number to yourself. No pen, no paper, just today's first law. Question 1. A system absorbs 200 joules of heat and 50 joules of work are done on it. What is delta U? 200 plus 50, positive 250 joules. Question 2. For nitrogen plus 3 hydrogen giving 2 ammonia, what is delta N gas? 2 moles of gas on the product side, 4 on the reactant side, so 2 minus 4 minus 2. Question 3. For 1 mole of an ideal gas, what is Cp minus Cv? The gas constant, Ra 2a. Question 4. Same change in volume, same two states, which does more work in magnitude? Reversible or irreversible expansion? Reversible every time. And question 5. The thinker. 1 mole of an ideal gas expands reversibly and isothermally at 300 Kelvin from 1 liter to 10 liters. Using R equal to 8.314 and the natural log of 10 equal to 2.303, find W. W equals minus NR, T times the natural log of 10, minus 1 times 8.3, 1/4 times 300 times 2.303. Approximately minus 5,744 joules, close to minus 5.74 kilojoules. If you carried that through, you have truly understood today's class. Let us gather the whole class in one slow breath. The first law says energy is conserved. Delta U equals Q plus WR. Heat flowing into the system is positive Q. Work done on it is positive W. Expansion work done by the system is negative. And reversible work is always the larger in magnitude between the same two states. Enthalpy is H equals U plus PB. At constant pressure delta is the heat of reaction. And for an ideal gas Cp minus Cv equals R. For gas reactions, delta H equals delta U plus delta N gas RT. Watch the sign of delta N gas, products minus reactants. Hess's law lets us add the enthalpies of steps to build one we cannot measure directly. And from bond enthalpies, delta H equals bonds broken minus bonds formed. Count every bond honestly, carbon dioxide hides 2. And next class, we go deeper into thermodynamics. Thermodynamics 2, entropy, spontaneity, and Gibbs free energy. The law that decides which way a reaction will actually go. Do not miss it. And so, my friend, we have learned to read energy's ledger, G style. It may have looked like just one equation and a handful of signs, but understand this. The first law sits beneath every heat of reaction, every bond enthalpy numerical, every Hess's law chain G will ever ask. Sarah, David, Lisa, and John all wrestle with that minus sign on expansion work, and once it clicked, reversible and irreversible work stopped being confusing and became two clean numbers to compare. Be patient with yourself. Tonight, revise the sign conventions once, slowly, one idea at a time. You will crack G. Of this I am certain. If this class brought you clarity, subscribe to the channel so the next one finds you. Until then, keep going. I will see you in the second law.